Hello, my name is George Keresidis and I'm from the Particle Technology Laboratory of ETH Zurich. Together with my collaborators, we are trying to quantify the contribution of black carbon to global warming. Here, I'm going to focus on the direct radiative forcing by black carbon agglomerates. During combustion, black carbon nanoparticles collide to form these fractal-like clusters that in my presentation I call agglomerates. As soon as these agglomerates are emitted in the atmosphere, they are coated by organic and inorganic compounds, as you can see in this microscopy image. Their climate impact is related to their direct radiative forcing, which can be obtained by multiplying their absorption aerosol optical depth by the radiative forcing efficiency. In this relation, the absorption aerosol optical depth quantifies the total light absorption from all black carbon emissions, and it is about 80% from the total absorption aerosol optical depth from all aerosols. So here I'm presenting you the absorption aerosol optical depth obtained for black carbon emissions only from the Aeronet network of ground-based sun photometers. Climate models that had been included in the 2007 and 2013 IPCC reports estimated the absorption aerosol optical depth of black carbon assuming bare spheres, so neglecting the coating of black carbon as well as its agglomerate structure. Due to this large oversimplification, these models underestimated the absorption aerosol optical depth by 60%. Of course, more recent climate models that are included in the most recent IPCC report account for the coating of black carbon. This coating enhances the light absorption of spheres through the so-called lensing effect and increases their absorption aerosol optical depth. However, this estimate is still 20% smaller than that obtained based on Aeronet observations. This indicates that current climate models might still underestimate the contribution of black carbon to global warming due to the neglect of its agglomerate morphology. So here, I'm going to show you how we can account for the agglomerate morphology of black carbon in order to reduce the discrepancy between observations and models. And we are going to do this using a discrete element model for coagulation and surface growth. For the interest of time, I won't go through the details of this model, but you can find more information in our 2017 publication in the Proceedings of the Combustion Institute. Using this discrete element model, we are able to derive the agglomerate morphology of black carbon based on the fundamental mechanisms of agglomeration and surface growth. That way, we found out that the mobility diameter of black carbon agglomerates, shown here in the y-axis, is related to the number of their constituent primary particles, that's shown over here in the x-axis, by this universal power law. So we took this power law and compared it to data from premixed planes, a cast generator, and a real diesel engine. The excellent agreement that you see here between this power law and all the data that I'm including in this figure indicates that the simulated agglomerates of black carbon nanoparticles have a very realistic morphology. So we used these realistic but simulated agglomerates together with the Rayleigh-Debye-Ganz theory to estimate their light absorption. Firstly, we used the refractive index that has been derived for carbon-rich black carbon nanoparticles. Please notice that the imaginary part of this refractive index is larger than the one that was commonly used in many climate models until very recently, and has been derived for hydrogen-rich nanoparticles. Furthermore, here we account for the enhancement of the light absorption of these agglomerates due to the light scattering between their constituent primary particles. In order to do this, we interfaced the discrete element model that I showed you before with discrete dipole approximation. So we estimated the light absorption enhancement for simulated agglomerates having a mobility diameter ranging between 50 and 250 nanometers and a primary particle size ranging between 7.5 and 40 nanometers. That way, we covered a large range of mobility and primary particle sizes that can be obtained at different combustion conditions. So we found out that the light absorption of these agglomerates is enhanced on average by a factor of 1.18. So we combined this enhancement factor with this refractive index and estimated the mass absorption cross-section of black carbon agglomerates, which is a key property to derive their absorption aerosol optical depth as well as their direct radiative forcing. We benchmark the mass absorption cross-section that we derived here with those measured for bare black carbon nanoparticles in lab flame reactors and diesel engines. The values that you see over here have been obtained by Bond and Bergstrom in their review published in 2006, as well as by Liu et al. In their review published in 2019. The mass absorption cross-section obtained by climate models assuming bare spheres underestimates the measured light absorption by 40%. Please remember that the mass absorption cross-section and the absorption aerosol optical depth are two distinct properties, and that's why we have a different discrepancy between data and models here. Now we wanted to benchmark our own calculations as well, so we also estimated the mass absorption cross-section for bare spheres. As you can see, our estimate is larger than the one obtained by climate models, and this is due to the refractive index that we used over here that has been derived for carbon-rich nanoparticles and is larger than the one commonly used by climate models. So by just using a more realistic refractive index for black carbon, we can reduce the discrepancy between data and models to 20%. And now if we also account for the agglomerate structure of black carbon, you can see that its mass absorption cross-section further increases. And this is due to the light scattering between the primary particles that make up this agglomerate. The mass absorption cross-section that we derived over here for black carbon agglomerates is in excellent agreement with those measured over here from different experimental datasets. So we combined this mass absorption cross-section with the atmospheric burden that has been averaged over the most recent climate model studies to obtain the absorption aerosol optical depth of black carbon. We did this firstly for bare, but also for coated black carbon spheres, assuming an average coating thickness that is suggested in the literature. As you can see, the absorption aerosol optical depths that we obtained that way are in excellent agreement with those obtained by climate models that make the same assumptions, but they are still smaller than that obtained based on Aeronet observations. Accounting for the agglomerate structure of black carbon increases the absorption aerosol optical depth for both bare but also for coated black carbon nanoparticles. In fact, the absorption aerosol optical depth that we derived over here for coated black carbon agglomerates is in excellent agreement with that obtained based on Aeronet observations. So we used the mass absorption cross-section that we derived over here for coated black carbon agglomerates together with a standard global climate model. For example, over here, you can see the global distribution of direct radiative forcing obtained by the ECAM-HAM climate model, assuming coated spheres. So firstly, we made the common assumption that is made in the literature. The dotted and the blue areas that you see in this map reflect changes of the direct radiative forcing that are not statistically significant. The direct radiative forcing of black carbon is positive and ranges between 0 and 0.5 parts per square meter in most regions of the world. However, there are still areas where black carbon emissions are very high and reduce large direct radiative forcings that range between 2 to 4 parts per square meter. These so-called hotspots include China, India, the Arabian Peninsula, and Western Sub-Saharan Africa. These hotspots have also been revealed by climate model simulations using satellite observations as an input. However, the direct radiative forcing that we derived over here for coated spheres is smaller than that obtained based on observations. Now, accounting for the agglomerate structure of black carbon increases its direct radiative forcing globally by 25 to 50%. In particular, at the hotspots that I showed you earlier, the direct radiative forcing ranges between 3 to 5 parts per square meter, and it is in excellent agreement with that obtained based on observation. This is a very important finding, as this very large direct radiative forcing can increase the regional temperature by 2.4 to 4 degrees. And with this, I would like to come to the conclusion of this work. Today, I showed you that agglomerates of black carbon nanoparticles absorb more light than single spheres due to the light scattering between their constituent primary particles. The mass absorption cross-section, as well as the absorption aerosol optical depth that we derived here for black carbon agglomerates, are in excellent agreement with those measured and observed from the Aeronet network. So we interfaced the mass absorption cross-section that we derived here for coated black carbon agglomerates with a standard climate model. And that way we showed that accounting for the realistic black carbon morphology enhances globally its direct radiative forcing by 25 to 50%. In particular, the large direct radiative forcings that we obtained at these hotspots were in excellent agreement with those obtained based on observations and could increase the regional temperature by 2.4 to 4 degrees. With this, I would like to thank you so much for listening, and I'm looking forward to meeting you at AAAI.